Hi everyone, and welcome to the MLOps Live webinar series, and to a very special session on a topic that has been getting a lot of interest from the industry lately, feature stores. My name is Sahar, and I'm the VP of Marketing at Iguazio. And for those of you who are joining us for the first time, this is MLOps Live, a webinar series dedicated to operationalizing machine learning and bringing data science into real business applications. Before we start, I'd like to invite you to join our growing MLOps Live community on Slack to connect with over 280 MLOps and data science practitioners. This way, we can continue the conversation after the session. We'll drop the link in the chat box now. Feature stores are becoming quite a topic of conversation in MLOps circles, and for good reason. The central place to build, manage, and share features across the organization simplifies and accelerates the path to production. Analyst firms like Gartner and 451 Research have been covering this topic extensively recently. In fact, just a few days ago, 451 Research released a new report titled The Feature Store, examining the rise of a new repository for machine learning, where they deep dive into this topic and the industry landscape. In this webinar, we're going to cover everything you need to know about feature stores. And to take us through this topic, we have Adi Hirstein, VP of Product at Iguazio, joining Yaron Haviv, Iguazio's CTO, and myself to break it down and discuss what feature stores are, what are some of the main challenges that they tackle, what the feature store landscape looks like today, and an example of a customer use case, the Sheba Medical Center, ranked as one of 10 top hospitals worldwide by Newsweek. Sheba is implementing AI across several clinical and logistical use cases, one of which is predicting COVID-19 patient deterioration in real time with the use of a feature store. We'll talk about that, and we'll then finish the session off with a live demo. We'll be running a short 2-question poll in between to hear about your thoughts on feature stores, so please do fill that in. These polls help us make these sessions as valuable as possible for you. And as always, we'll share the results at the end. Also, feel free to ask us any questions you might have in the Q&A panel at the bottom of your screen, and we'll do our best to address them all during or after the presentation. We've now put everyone on mute, and we're recording the session so that we can send it to you afterwards. I will now pass things over to Adi to get us started.
Okay, thanks, Sahar. Okay, so before I go deep into the feature store, I'd like to start with some of the key challenges of MLOps in general. So we know that organizations are investing a lot of resources in machine learning, but they're facing huge challenges. You have multiple teams working on those machine learning pipelines. You have data scientists, data engineers, DevOps, lots of back and forth between the data scientists and data engineers in order to take your model to production. Then the production environment is very different than your training environment. In production, you need to take care for monitoring, security, performance, scalability, all kinds of things that doesn't really exist in your training environment. And then you have to deal with the data. So this session today about the feature store is all about dealing with the data, dealing with the features. So how do you manage those features in your training environment and production environment in a way that's going to be efficient, and you can take those features all the way from development and research environment to production? And then last but not least, when you have a model and you deploy the model in production, how do you make sure that the model is running properly? How do you do model drift? And if you identify that there is a drift, there is a deviation, how can you trigger everything again, the entire pipeline, in order to create a new model and deploy it back in production? So those are the key challenges that we're seeing. So we have the data basically as the main issue when we are creating those machine learning pipelines. So we have data that is in the databases. We need to create processes like ATL and streaming, and we need to get the data using all kinds of APIs in order to get the data into the online store and the offline store. We have data scientists that are working on those different databases in order to explore the data, to run the processes, to run the training in a batch manner and an online fashion, and basically monitor the data that resides in the online store. Now, when we think about the data in the context of machine learning, we're actually thinking about features. So what is a feature? Feature is basically a piece of data that is going to be consumed by a machine learning model. And in a very high level, we have two types of features. We have static features, like let's say that I have users as an entity, and this user has all kinds of information on it, like the address of the user, country, language, education level, those type of things. Those are features that don't change too much. And then we have features that are more dynamic, that needs to be calculated, like max purchases, and max number or total number of impressions and clicks, and so on and so forth. And those features basically need a processing engine to generate and to calculate those features. Now, in some cases, we even have more complicated features. So, for example, if we want to analyze a sentiment analysis, we may use another machine learning process just to generate yet another feature. And this feature is going to be part of a wider feature set in the feature vector, which is part of a more complex pipeline, basically. So feature engineering is a big thing, and customers are investing a lot in order to create those features. And how do you create those features? You're taking raw data from your databases, from your streaming engine, and basically you need to apply all kinds of processing in order to create those features. So you need to create aggregations, things like max, mean, count. You need to filter the data. You may need to transform the data, calculate all kinds of things like z-score and others. And you may need to join the data with different data sets. Once you do that, then you have the features in place, and those features can be served in your training environment, in your serving environment, and also there is a notion of monitoring. So you need to monitor those features. It's not just about monitoring the models, but you actually need to monitor those features in order to see if there is a deviation. So organizations are putting lots of resources in order to create those features, lots of trial and errors until you get to the final stage where you're happy with your features, and those features are actually ready to be deployed in production. So lots of work around creating those features, synchronizing between those features that are in the training environment and in production environment. And then the last part of monitor featuring is also a pretty big challenge. Now, in a typical case, in a typical enterprise environment, we have a couple of layers. So we have the research layer, where we have data store like a data lake. Then we have the data scientist comes in and basically start exploring the data, taking the data out of these data stores. So when he explores the data, he needs to create those features. Usually, he runs all kinds of batch transformation, putting those features in an offline store, and then create the model out of it. And it's very a repetitive process, so you need to do it again and again. Once it's ready, you need to take it into a production environment, which means that you need to deploy everything in this production environment that is very different than your training environment. So in production, you may have some online databases, so you need to create an ETL processes that knows how to take the data from your online databases. You need to basically transform the offline processing into an online processing. It means that all the transformation now needs to be sometimes in real time, in an online manner. And then you store the data and analyze the data in an online database that can be consumed by your model that is running as an online model serving. And in addition to that, you also have this govern and monitoring layer where you need to monitor the model itself, obviously, but also generate statistics around the features so you can basically run all kinds of reports, slice and dice the features, figuring out if there is a deviation in those features. So when a data scientist starts working on a project and now he has a model in place and he wants to deploy it in production, he basically needs to go back to the data engineer, and the data engineers needs to figure out how we can basically start creating those ETL processes, try to duplicate what the data scientist has done in the development environment and do the same thing in production. So it means that they need to re-implement all those processes that have been done in the the research in the production environment. Not only that, now we have the MLOps guys. He needs to take care that the runtime in production is ready. So you have everything that you need in order to run your machine learning models in production. It means that you have the right set of images, libraries, environment variables. You need to containerize the code and the machine learning model that you have in your research environment and put it in production so it can run at scale. So this process is a very resource-intensive process. You have multiple teams working on it, data scientists, data engineers, MLOps, and in many cases, they're working in different groups, different business units, working in silos, basically. So that makes it very, very challenging. And this is where the feature store comes to the rescue. So feature store basically solve the hardest part of machine learning pipeline, which is the feature engineering. And that's why it's so powerful. Now, what is a feature store? Feature store, first and foremost, is a single pane of glass where you can manage all of your features. So think about it. When you, as a data scientist, when you start a new project, you want to see if the features that you need already exist. So feature store allows you to basically have a single pane of glass where you can search your features. You can quickly analyze if those features exist. And of course, if they exist, you can reuse those features and you don't need to start from scratch. Now, a feature store also provides you all kinds of statistics on those features. So you can see which features are being used, which features aren't being used, which features are linked to which models, and what's the impact of those features on your models. So it provides you a very comprehensive view of the features, the entire set of features that you have in your organization. Now, the other thing, which is even more powerful than just managing the features, is that you're getting a very robust data transformation service. So Feature Store provides you the ability to create this feature engineering part, to do things like aggregation, transformation, filtering, all kinds of data manipulation, but in a very, very easy way. So you have a simple SDK, Python SDK, that really simplify and abstract all these feature engineering processes that you typically need to do, and the feature store under the hood basically runs them. So under the hood, the feature store knows to leverage tools like Spark or Dask in a distributed way, so you can create your features and do it at scale. Now, one of the most important things with the feature store is the fact that when you create those features, you're actually creating those features once, and they're immediately ready for a production deployment. And that's a big thing because you don't need to re-implement the code again and again. The data scientist doesn't need to go back to the data engineer, and they don't need to re-engineer the entire ETL process in production. And that's a pretty big thing. Another thing is that a good feature store is also integrated with the model monitoring. So if you think about it, if you can link between the monitoring of your model and the features, that provides you a lot of options to identify model deviation or model drift. So for example, if I train my model and one of the features was age, for example, and I was expecting to get an age range between 20 and 40, but the reality is that in production, most of the users are actually 50s or 60s, then I can immediately see that there is a deviation here. There's a gap between the features that was trained in my training environment and the actual features that are coming into the inference layer. So when you have that type of integration, you can quickly identify that. So feature store at the end of the day provides you the ability to accelerate your time to market because of the fact that you don't need to re-implement. You don't need to do all those engineering part and the MLOps part that I mentioned earlier. So the big players, they actually developed the feature store on their own. So we have Netflix, we have Uber, we have Twitter, and they already figured it out. So, so they developed a feature store because they understood that this is something that can really accelerate their ability to create new machine learning models that are based on a feature store. And what we're trying to do basically is to spread the word out and take this feature store into the enterprise, into other customers. So I try to map all those leaders in that space. And we can see that, there are a couple of companies here. We have Iguazio, we have Tecton, we have Fist, which is an open source. We have Amazon that recently announced their feature store. We have HopsWorks, and those are the leaders in that space. Obviously, we're going to see more and more commercial offering coming up in the next few months or so. But I think those are the leaders in that space. So when we think about how to pick and choose the right feature store for us, I think there are a couple of dimensions that we need to look at. So for example, are you looking for an open source versus just a commercial offering? So for example, Iguazio provide an open source, Fist is an open source. Another notion is whether the feature store support real-time streaming. So we're seeing more and more use cases around real-time, like fraud detection, predictive maintenance, location-based recommendation, those type of things. And the integration of a feature store with a streaming engine, a real-time engine, is also an important point. And we can see that solutions like Tecton and Iguazio support that. Another aspect is whether your feature store, whether you're looking for a standalone feature store or a feature store that is integrated with a full-fledged data science platform. So Tecton and Fist, for example, they are a standalone feature store. On the other hand, OpsWorks and Amazon and Iguazio provide a feature store that is part of your data science platform. And then the other aspect is the deployments. Are you looking for cloud, for on-prem? Some players are cloud only, like Tecton and Amazon, for example. And then some players like Fist and HopsWorks and Iguazio can basically run anywhere in the cloud and on-prem. So when we think about the key features within the feature store, those features that we want to look at when we look at a feature store, I think one of the most important things is whether the feature store provides you this robust data transformation. So that's really the power of it, the ability to run all kinds of feature engineering, aggregation, filtering, all kinds of operational stuff that needs to be done in order to create features out of your feature store using a very simple SDK. So you don't need heavy lifting on the data engineering side. You can actually do it in a very easy and abstract way as a data scientist. And that's really a powerful thing for a feature store. Another aspect is whether the feature store supports streaming cases. So if you want to support real-time use cases, you may want to have your feature store supporting streaming like Kafka. You need the ability to create a serving graph out of it. So that's another key point. And the other point is that you're looking for a native Python environment. So you can pick and choose your processing engine, whether it's Python, Spark, or Dask. That's very important to have that flexibility. The other point is a feature store should be integrated with the monitoring environment. So as I mentioned earlier, if you have this integration with the model monitoring, you can easily identify whether you have drift in your features, basically. Another point is the variety of data sources. You want to have a feature store that can support structure and unstructured and streaming data. And last but not least, you want it to be easy, right? So we want a single interface where we can easily manage the features in a very easy way. Okay, so to summarize, feature store is, in my mind, is the real deal. And it's really solved the hardest part of machine learning, which is the feature engineering. And that's why it can really accelerate time to production. So everybody is saying that they can do that, but a feature store can really do that because of the fact that it provides you a very simple way to do the feature engineering in a very abstract way. So as a data scientist, I don't need to go to the data engineers to build those features. I can build the feature once, and those features are actually ready for production from day one. And this is how we can really save time, because there is no re-implementation and recoding of those features once you move from development to production. Another aspect is that if you do that with a feature store and you don't need to re-implement the code, it basically means that you're avoiding the risk of training and serving skew, because you're using the same logic, the same code in the training and in production, so there is no potential skew here. And then the last point is the fact that the feature store is integrated with the model monitoring, which means that it's ready for production from day one. You can quickly identify if there is a drift, and by doing that, you're getting a full-fledged capabilities of creating those features in production. So because of all those reasons, I truly believe that the feature store is a must-have component for any machine learning pipeline. It really solves the hardest part of machine learning, which is the feature engineering. And that's why it's something that I'm sure that we're going to see in every machine learning pipeline down the road. So that's pretty much it on my end. Back to you, Sahar.
Thanks, Adi. So we're now going to move to the second part of the presentation, where Yaron is going to speak about the Sheba use case and take us through a demo. We see it.
Great. So I'm going to explain a few words just on the Guazio's feature store, and then we'll go through a live demo of all of those things. But in essence, what Adi was mentioning, that the feature store comprises of two base elements. One is essentially a cataloging mechanism where every time you ingest features or you consume features, everything is listed and versioned in some sort of a catalog. And also all the automated transformations for whether it's the ingestion part or the consumption part. There are essentially two different analytics pipeline being applied. One is to generate the features, and the other one is to essentially join and time travel the features into a feature vector. Because when you're selecting features that come from different data sets, someone needs to combine them into a feature vector and align them on the right timing and join on the right keys and so on when you want to abstract it away from the user. So there are essentially two different objects, main objects in a feature store. One is a feature set, some may call it feature groups. It's essentially a set of features that are generated together. Early versions of feature stores didn't have that concept of grouping of features, and that essentially they calculated every individual feature using a different analytic pipeline. It created a huge amount of effort for everyone. So the general idea is that you compute the set of features together and you call it a feature set. And then feature vectors are those things that we assemble from multiple features, and we use them for training, for serving, for monitoring, and so on. So to generate the features, we essentially need to build a feature set and a set of transformations. Usually the way that we build a feature set or the features, we have one type of source. The source could be an online source like a Kafka stream, could be an offline source like a table in some operational database, or a Parquet file or CSV file. And then we want to write it to different sort of material views or different type of persistency stores. Usually you at least having something which is more real-time, like a NoSQL database, and something which is more like a data warehouse or a Parquet file for training. But that's not necessarily the only options, especially in our feature store. We support many different options, including storing to time series database, which allows you essentially to view features on a dashboard with zero glue logic code, or writing features into a stream. So in many push-oriented scenarios, like if you think like many scenarios, you don't want to go and query the feature store. You want a feature store to go and push a vector into a destination. So in those cases, we may use stream as an output of a feature store, not necessarily just as an input. And when you're building those feature sets, you need a transformation. You have a source, you have a set of transformation. You see here an example. We'll see that later in the demo done through the code, but it's nice that you can toggle code or through a visual UI. And then after the transformation is being written, all this mechanism is built on the serverless engines, part of the MLRun project, which is open source. So for real time, it's using Nucleo, which is a real-time serverless engine, or Spark for streaming. And for batch or offline, it's using various engines, also part of the MLRun serverless framework, either Spark or Dask or Kubernetes jobs and so on, everything that's supported under MLRun. But you don't need to know all those details. You'll see that the serverless functions are essentially generated for you based on what you're trying to do. It will automatically generate the right functions for you. So this is, again, this is the feature sets and how we can produce them. Now, once we've produced the feature set and all those features are marked and labeled, and you can see if they're materialized or not, and in what kind of storage they're materialized, then those features, they're automatically also being analyzed for deep statistical analysis and metadata inferencing, and you have data quality and data validation rules applied to them and all that, again, automatically. So it's not just storing a feature. The features are already stored with a lot of extra information that will be used later in the pipeline, like the statistical analysis, which is done on the online and offline statistics, features, is later used to identify drift and accuracy problems in your model without writing a single line of code. Okay, so once we created those feature sets, we can start and go and just pick and choose from sort of a catalog features from different feature sets and build those feature vectors. And we can just name those feature vectors and then use them in the code. If we want to use them for training, we just go and read those feature vectors and convert them to like a data frame and run some analytics, some sort of training job on top of them. Or we may use them for real time. In real time, it's essentially you need to initialize the feature engineering pipeline, and then you're reading directly from the processing engine. Iguazio underlying architecture has an extremely high performance key value store, which also knows how to do transformations. So what's unique about the real-time feature store in the Iguazio platform is that you can essentially create a feature vector in less than a millisecond. So if I'm sort of throwing this patient ID at the feature store, I'm going to get the feature vector in less than a millisecond. It's faster than in-memory databases. So that's also very powerful. And finally, we can also build using, again, the MLRun framework and serving framework and real-time pipelines. You can essentially build production pipelines that go beyond just doing data engineering or model serving or simple model serving. You could build things which are extremely complicated, that do various transformations, build ensembles across multiple models, do post-processing. All that could be built in couple of dozens of lines of code. They could be tested on your notebook. And then once you want it to run in production, it's a single line of code or a single button in the UI, and you essentially have a fully production real-time pipeline. So that's important. Now, when you create those real-time pipelines, it's important that it's not just doing the serving. So obviously the serving pipeline need to access the feature store, get the real-time features, along with things like validation rules. So sometimes you don't really want to do the inferencing. You want to fail it because the features you're getting are poor quality. Maybe someone is trying to abuse your service and put wrong parameters. So you want to block it already here. But everything you're serving, all the information is written to yet another stream, and that's automated with the the MLRun serving framework. Every output goes into a stream, and then you have essentially a real-time stream processing set of functions that do the statistical analysis on the real-time data. They compare the statistical analysis with the training statistical analysis, and they also write back the features into the feature store, the operational features, the real-time features that have been produced in the production pipeline are written back and could be reused later. And those, you could, again, look at various nice screens that analyze this production data, or through Grafana plugins that know how to analyze this operational data. And if you identify things like drift and accuracy problems, etc., you can essentially trigger a notification, which will, those notifications, you could retrain your model to improve its accuracy and so on. Now, this is something very important, because if you start working with independent tools for feature store, for model monitoring, for model deployment, for training, and so on, you end up doing all the integration. What's nice about this approach that we pioneered with MLRun, which is an open source project, is a holistic implementation where everything is glueless, as I'm going to show you in a minute. This is just an example of how we can analyze those features in real time and compare the sort of the production features and historical features. Now let's take this example, which is it's a real example. It's actually deployed, but I've taken a subset of this example just to show you. Let's assume we have 3 different data sets. Okay, some are real time, some are frequently changing, and some are relatively static. So assume we have a patient records. Patients records don't change much. You have an age, a date, and other information about the patient. You have other data, like a patient took some blood sample, and you have the results of the blood sample or some other type of measurements. And you have real-time sensors coming from the actual patient bed. Like I have real-time heartbeat, movement detectors, and all that. And again, this is all real data. I'm going to use a simulated data for the sake of a demo, because again, patient data is very sensitive. But this is all based on a true deployment. And here you see the nice thing about this, the feature store, is that you can use different engines that fit the different use cases. So we can use Spark for things like batch, transformations, for things that are very rich on like data frame transformations. We can use MLRun with Dask or just regular Kubernetes job for periodically just launching a job, reading some external table or file, or interacting with the medical record database and ingesting it into the feature store. And when it comes to real-time performance, where essentially we can listen on a stream, in this case it's Event Hub in reality, but could be Kafka or Kinesis or any other stream that's supported by Nucleo, and it will ingest the real-time sensor data into the feature store. Once it's there, we could just go and do some interactive exploration. But the more interesting thing, we could build an entire pipeline on top of it. So we can fetch the features and essentially create a training set. We can use AutoML to build the models. And then we deploy the models using the Nucleo serving framework and into real-time pipelines. And the real-time pipeline actually talks to the feature store to obtain the real-time features and validation rules and respond to that. But it's not all. Essentially, what we also want those Nucleo serving functions to do is push the streaming information from what's happening in production into the model monitoring framework. And that model monitoring framework writes, again, the data into the feature store. And someone could just start building additional analytics application to run explainability logic, analyze all the behavior of the production data, and so on. So you have a fully fledged solution, all fully integrated, where the feature store is the center of this universe, and again addresses your entire life cycle of machine learning. So with that, let's move to a live real demo. Sorry. Okay, so let's look into essentially I have 3 notebooks here. The ingestion part, how I'm building the feature sets and creating the features. Then we're going to look into how we're doing the training, and then we're going to look into the serving and monitoring. So let's start with this example. So essentially what we said, we have several different data sets. Here we're going to show 4 different data sets. The measurements, the real-time sensor data, the patient records, but there is also a 4th data set, which is the label data, because when I'm doing training, I also need some data labels. And that's interesting that you can actually create a feature set of the labels and join it for the training, and we'll see how we're going to do that. So the first thing that we want to do is use Spark. A lot of people like Spark, and let's assume we want to build a pipeline, which starts with some source. Again, we said that all those transformations, we start from some source. The source could be a real-time thing, like a Kafka stream, or it could be just a simple file. Like in this case, it's a Parquet file that has some patient measurements. So I can just go and define a pipeline where the source is this Parquet file. I have some transformation, which essentially gets the Spark context and the MLRun context and a source data frame, runs something, and returns a data frame. But after we have the data frame, we essentially want to write the result of the data frame to the different data stores. We also want to run the inferencing on the data, which is essentially doing the statistical analysis, schema inferring, and all of that automatically. So the only thing we need to say is just ingest data with Spark, with the Spark context. This is the feature set that we just created called measurements with Spark, because I have two implementations with Python and Spark. The entity is essentially the key that's used for that data set. And then I'm just going to ingest that. The source is this Parquet. I want to infer all options, meaning statistics, histograms, schemas, and so on. And this is my transformation function. And this thing will just run against some Spark and creates material views of the results in both NoSQL and Parquet, because that's the default definition of that feature store. I can do exactly the same using Python. It will be slightly simpler, just again defining this feature set, creating ingestion pipeline. And again, this is the result. The result of my ingestion pipeline is essentially what I pushed as a source. Why do we have results and source? Because you'll see in a second when I'm starting to do something more interesting with the data, all sorts of transformations. So this is how I ingested the very basic feature set without any transformation. And I could use two different tools. I could use my notebook from using pandas, or I could use Spark job from my notebook or as a standalone job. Now let's do something more interesting. Let's assume we need to do a bunch of transformations on top of our data. We want to do one-hot encoding, value mapping, imputing, and so on, different types of transformations. So this is where we're using a new engine that we've developed for like stream processing using Python. And it's essentially, you build a graph, a pipeline of different steps. This graph has sort of a pipeline that starts with the mapping, the one in encoding and imputing. This is essentially how it looks. At the end, it writes to those two different targets. So again, my definition of the graph is extremely simple. Every Python guy can do it. Those classes could also be Python classes. They don't have to be pre-baked classes that we have in the library. You could build your own classes for data transformation. You could, you can point you later to the documentation and see how you can do that. But there is a library of many different types of transformations and aggregations that's already pre-built for you. Again, I could just go and plot my pipeline to see that it's doing what it's supposed to do. And then I can infer my pipeline, which essentially builds my pipeline in memory, runs it, and I can see the results. This is very powerful because I don't need to go to Spark. I don't need to go to SQL and all of that to understand what's going to be the result of my feature engineering pipeline. I could just throw some data at my pipeline, see the results in my notebook, and you know what, maybe I forgot another step. Maybe I need to change something in my transformation pipeline, and then I just go and do that again. Once I've done it on a subset, I can just go and use the ingest. I can save my feature set, and I could run ingestion, full ingestion for the entire set of data, and it will run through the entire data. Now, this was all running from my notebook. What if I want to run the ingestion pipeline on a schedule using some containers on Kubernetes? Okay, so now I need to take everything I did and transform it to containers and YAMLs and all of that. But using MLRun, I don't really need to do that. I can just go and convert my feature store or my feature set into a production pipeline. So, or a real job. So here I'm just, I don't really have to do it, but I had to use here some custom image. So I added another line. So it's not 2 lines, it's 3 lines. I'm using this source, this Parquet source, as a source of my pipeline, using my feature set, the one that I've defined. I'm running it as a job, and then it could just run on a Kubernetes or locally. It will create the Kubernetes pods. It will launch it as a job on the cluster, and collect and write the results into the feature store. So here I can even specify schedule rules. Every day, 1 a.m., go run ETL pipeline from my Oracle and ingest it into the feature store. And this is done in essentially 2 lines of code. The next thing I may want to do is run another pipeline which is more real time. What we've seen until now is pipelines that are more batch oriented, taking a file, ingesting it, maybe doing it periodically, maybe reading it from a database, but it's still sort of batch. Now let's take the features set, which is the real-time sensor data coming from the patient's bed. Okay, so here, let's create this early sense, sort of the sensor data. Again, patient IDs are key. This one has a timestamp. We may actually want to define some data validation policies, like heart rate cannot exceed those values probably. If it does, we want to get alerted. And we could specify a bunch of data validation rules as part of our pipeline. We could also go and start build classes that we'll use in our Python in our pipeline. This is like those are also library functions, but we wanted to show here that you can just add a class for dropping columns, a class for renaming columns, and so on. So you could build your own classes that will be injected into the pipeline. And in here, I can just, again, build a graph. This graph needs to drop columns and need to rename columns, okay? The other thing that's very, very important for time series information is to build aggregation. So now I want to take all those different sensors, like respiration rate, heart rate, movement sensors, and so on, turn count sensors and all that. And I want to start building aggregations on top of those. So if I would have to do this thing in SQL, that's probably like 300 lines of code in SQL. What I'm doing here in 3 lines, a very higher level implementation. And this code will run either in the production pipeline, the real-time pipeline, or the batch pipeline. So I define it only once, given its abstract classes. It knows how to translate itself to the different real-time or batch pipelines automatically. Now, when I'm going to plot my pipeline, you can see that I essentially have a pipeline that drops column, rename columns, aggregates, and finally writes to Parquet. If I want to simulate my pipeline, you could see that I'm throwing some data at my pipeline, and you see all those aggregations, the daily averages and hourly averages, and all the other things I specified are visualized here. So again, I don't need to go to any data engineer. I don't need to go and debug it on a different framework. I just do it on my notebook. If I don't like the results, I go back to the pipeline, change a few lines of code, rerun it, and see that it works. Now that I have my pipeline, I want to run it as a real-time pipeline. And in this case, I need to use real-time ingestion function. So I have to deploy a real-time ingestion service. And so we use, in Amaranth, there's a concept of converting your code automatically into a microservice function. So this code to function thing here will essentially goes into my notebook. You remember we had some code here. It will identify the code markers to essentially automatically convert the code from my notebook into a microservice that runs in production. So again, one thing I had to do was code to function to convert my code from the notebook into a microservice function. And I just need to go and deploy that. So this thing will actually go and deploy a real-time function. We can actually see that function in the Amaranth dashboard. You'll see that actually, remember this code that I had in my notebook, it was automatically exported into a real-time function that is running this ingestion pipeline. And by the way, this function I could specify through the API, not just HTTP sources that I've defined. I can also specify Kafka, Kinesis, Azure Event Hub, whatever other type of data source that I wanna use. Okay, and this is also auto scaling, so I can define like GPUs and CPUs and scaling thresholds and all that again through the API. I don't have to use the UI, and this will automatically deal with whatever workload you give it. It's going to scale automatically to address any kind of workload that you have. So you see, again, very easily, I created a real-time pipeline by specifying maybe a dozen lines of Python code. And lastly, maybe I just need to ingest the label. Again, assume that's coming from a different source, but I want to just ingest the label set, the label data set. So here, essentially, now I have all those features. If we go into the feature vector, we're going to see that we have all of those features that I've ingested in the feature store, and I could build the feature vectors out of all of those feature sets. So now going into the next notebook, I want to run training. So in this case, I need to take a bunch of features. You see, like from every feature set, I can take one or more features. I can use asterisks or some other, like any annotations, etc. But here I'm just specifying about 50 different features. Note that they're from 4 different feature sets, including the labels. The label is another important thing that I need for training, but I don't need the labels for serving, obviously. So that's only used in training. So I created the feature vector and I just saved my feature vector. Okay, now if I want to get my feature vector, I can just go and read this feature vector object here and convert it to a data frame. And that's it. I have all those different features that we specified, all those 50 something features that we've specified are joined together, leveraging concept of time traveling. So they're all joined together at exactly the same point in time that you need to use them. And if we want to export that into a file, no problem. We can just go and export that. Or if we want to now run training job on top of it, then again, we're just going to load the training function using the MLRun service. We're going to specify to that training function the feature vector name, which is FS demo project, patient deterioration feature vector. Give it some other parameters like the label and so on. We want to run a bunch of different models. So this is a AutoML training function, and one of the things that you could tell it is give it a list of different algorithms or parameter combinations to run. So here I want to generate 3 different models for logarithmic regression, random forest, and AdaBoost. Okay, so here the only thing I need to do is run this thing, which is consuming the feature vector which I just generated and generating those model objects. So again, this is going to run. It can run on the notebook or as a Kubernetes job. Again, just the same using the MLRun technology, and it will choose the best model. So all those models are going to, again, be stored in the model repository of MLRun with all the metadata and all the configuration of that model, and I could just go and use them. When I'm running those training jobs, back. So all those ingestion jobs are also, I can just go and see them in the MLRun UI. So, you remember it was AutoML, so I can see those 3 experiments and I could see the accuracy of each one of the executions and, all the logs about this specific execution. So again, what we've done here is we've created the feature vector from a set of features from the feature store. We ran training and we generated 3 different models that are stored now in the model repository. So the next thing we want to do is build a serving pipeline. So here we're going to build a custom serving function, although you don't really need to do it. You have in the library, you have built-in serving functions, so you can just import them. But just for sake of understanding how it works, you use MLRun serving engine. You build a classifier model which inherits the model serving engine. In the load of the model, we can essentially go and load this feature vector, and then every time we get a request in the pre-process hook, we essentially enrich the feature vector from this patient ID that came in the request, and then we predict. So 3 simple steps, and we essentially serve the model. In order to define something slightly more complicated, like an ensemble, we just need to set the topology for our real-time pipeline. In this case, it's a router topology. And we define an ensemble of 3 different models. You see, we defined here an ensemble. We added 3 models under the ensemble router group. And we could create a simulator in our notebook. We can feed the simulator in our notebook of the serving engine. We can just feed it with our training set and run it again on the notebook just to verify that it works properly. So we can do that using a few lines of code. And once we see that it's working, we can actually go and deploy our function. So we could just run, we give it a mount point, so it will have access to the model files, and we just deploy, and that will generate a real-time endpoint for serving our models. Okay, so if you go into the function, the Nucleo function, you can actually see this code, and this function is listening on a real endpoint and can intercept our request and respond in real time with all the feature vector data. Now, beyond just responding, now we said that everything is automatically monitored in using the feature monitoring. So all that, the same data that we generated is all those 4 models essentially, because you have the 3 individual models and you have the ensemble model, which is the result of the entire thing. All of that is being monitored by the model monitoring framework. So you have the full loop of creating the features using any tools that you've seen here, Spark, Kubernetes jobs, Dask, Nucleo for real time, and so on. You have the ability to build a training set, very complex training sets using a single line of code, run it through AutoML using a few more lines of code, and building the full real-time serving pipeline with a few extra lines of code. So what I've showed you here is usually something that will take a few months for a machine learning group, and it will involve data engineers, data scientists, DevOps, Kubernetes people, and so on. But you see that using this technology and leveraging the feature store as sort of the anchor, that everything revolves around it. The data preparation logic writes to the feature store. The training reads from the feature store. The serving reads and writes to the feature store. The training, again, reads and writes to the feature store. Now you have something which is much more straightforward, much more automated, and much more managed. So people can just log in and access the features, choose them from a catalog, build a new model without essentially starting from scratch. So that's all from my end. I'll stop sharing now.
Thanks, Yaron. That was wonderful. Right. So this has really been a jam-packed session. We've been answering questions on the Q&A panel. I think we got through most of them, and we'll just maybe take 1 or 2 more because we are nearing the end of the session. So let's see here what we have left. So there's a question here on Azure ML and whether the solution works with Azure ML. Yaron, would you like to take this one?
Yeah, sure. We've already demonstrated in a few places. Also, there's actual customers. The Sheba Medical Center is actually using Azure ML. A few other large enterprise customers are using Azure ML with the feature store, with our feature store. So essentially, it's fully supported. We know how to use the AutoML capabilities in Azure ML and automatically push the feature vectors into Azure ML and consume the models from Azure ML and deploy real-time pipelines using them. If anyone wants a live demo or talk, I'm happy to facilitate.
Excellent, thanks. And there's another question here. Can you please explain success criteria of models? Maybe you can say a few words about that.
Actually, I have a session on that on Thursday, I think in AI Camp something, Sar.
Yes, that's right, AI Camp community. We'll be sharing that on our LinkedIn channel on Thursday.
Yeah, so. We've done another webinar on that in our show. But there are different ways of analyzing the success of a model. a lot of it is related to data. You have what is referred to as the concept drift, which is, think about it, let's assume that you're training your model on a certain buying pattern of customers, and you have some average purchases per customer, average sum of purchases, and so on. And now, as you go into production, the buying pattern of the customer is different than what you were trained on. So that, by definition, it means that your model is going to be inaccurate, because if it was trained on some numeric values and it's serve an equation, it will generate some numeric values, and in production it will get different numeric values. So obviously it will generate different results. So that's what is referred to as concept drift. And you need to do this analysis on two things. One is on the input data, on essentially the feature vector, and the other thing is on the actual predictions and compare their behavior with the label data. So that's one thing that you need to analyze with your model behavior to see if there's no drift in the data. The other thing to analyze is the actual accuracy of your model. So you need to measure real, let's assume you're predicting the financial market behavior. At a certain point, you're going to know if the stock price went up or down. So you have labeled data in some sort of delay, or you're predicting churn of a customer. At a certain point, you know if the customer churned or not. So if you take the data and you move it back in time, you actually you can compare the prediction results with the real results, and this way you can measure the accuracy. So those are different techniques of measuring the performance of your model.
Excellent.
So if you want more details, then join my session on Thursday.
We'll just take one more question live, and Adi is continuing to answer here on the Q&A channel. So I hope we'll get to all of them. Do you support deep learning and NLP use cases?
Yeah. So one of the unique things about our feature store is that it supports not only machine learning. Most feature store are built around Spark, and Spark is great at running tabular data. But because we can build very versatile pipelines that have different steps, so you can actually integrate deep learning into your pipeline. So we have one of the financial customers that we have is building document analysis into the feature store. So essentially, you can read SEC filings or financial documents. You could use BERT models to break things down to like paragraphs, do entity detection, sentiment analysis, and so on those documents, and build those as features that are fed into the feature store. We also have other examples of working with images and video feeds. So the feature store is not limited. Our feature store is not limited to numeric and tabular data.
Excellent. So this has really been a jam-packed session and lots of questions. It's amazing to see how much interest this topic gathers. So we really do hope that you enjoyed the session. Before we share the poll results, I would like you to just know about our website, and specifically the section that we have on MLOps, and invite you to learn more about bringing data science to production on our website. In our MLOps section, you can find previous sessions of this webinar series, blogs, videos, and other resources to help you simplify and accelerate your path to production. And you can hear from AWS, Siemens, NVIDIA, S&P Global, Netflix, Twitter, and other industry leaders about their experience in operationalizing machine learning. I will quickly share the poll results with everyone now. So our first poll was, what is your biggest challenge around feature engineering? And 32% of you said complex use cases such as unstructured data, deep learning, NLP, etc. That was followed by teams working in silos at 19%, and then people who are not currently working on feature engineering at 18%. After that, the other challenges were in-house skill set or manpower, the time that it takes to engineer features, and a very, very small 4% of you said that you are working on feature engineering but don't currently have any challenges. Lucky you. And I'll now share the second poll. Do you currently have a feature store? So 58% of you are actively looking for a good solution. 26% don't currently have the need, and 16% are happy with the current solution. So thanks again for taking part. And that concludes today's session. We invite you to continue chatting with us in our community. We'll go ahead and share the link in the chat box again now. And if there are any questions that we didn't get a chance to address here live, please do get in touch with us over Slack, and we'll be happy to continue answering any questions you have there. On our next MLOps Live session, we'll be discussing automation and data governance with Microsoft. So make sure to join us for that. And at this point, I want to thank everyone for staying a bit longer than expected. So thank you for staying with us these extra couple minutes. And thank you, Adi and Yaron, for a really informative session. This was wonderful. It was great to be here with all of you. So thank you, and see you guys next time.